Welcome folks, a video today on bases. So we'll give a definition for a basis. We'll see how to find a basis for a span of column vectors. We'll relate bases to non-singular matrices, adding to our list of non-singular matrix equivalencies. And then we'll see how orthonormal bases are the bomb. Okay, here's the definition of a basis. A set of vectors S, that's a subset of the vector space V, is a basis if it's linearly independent, and a spanning set for V. So there's sort of two things to check here if you want to check if a set is a basis. First, you need to check that the set is linearly independent. And second, you need to check that the set is a spanning set. So start with an example. Here's an example. The set of standard unit vectors for Cm. The ith such vector has a 1 in the ith position and a 0 everywhere else, is a basis for Cm. So to see this, we'll show that the set is linearly independent, and that's pretty quick. So here's a relation of linear dependence on the set B, alpha 1 E1 plus alpha 2 E2 all the way out to alpha m Em. Of course, if this is equal to 0, then alpha 1 has to be 0 because that's the only element in the first location. Alpha 2 has to be 0. That's the only element in the second component, and so on and so forth. So we see that all the alphas must be 0. So to see that B spans Cm, we'll let x be an arbitrary element of Cm. X is, x1, x2, all the way to xm. We can quickly write this as a linear combination of these unit vectors. X is equal to x1 E1 plus x2 E2 out to xm Em, and we quickly see that B spans Cm. So the standard set of unit vectors is a basis for Cm. As an example, I'll have you work out on the worksheet that the vector space Pn has a basis 1, x squared, all the way out to xn. So again, this takes 2 steps. And again, those 2 steps are to show that B is linearly independent in Pn and that B is a spanning set for Pn. So I'll let you work that out on the worksheet. Here's another example similar to the set of standard unit vectors in the vector space of column vectors. The vector space M sub Mn has a basis. This is the standard basis for Mn, containing the matrices B sub Kl, where the matrix B sub Kl has a 1 in the kth row and ith column, and 0s everywhere else. So just to illustrate what that would look like, the standard basis for M22 is the following for, air quote here, vectors. We're sort of thinking of these matrices as vectors. Okay, so these 4 vectors are a basis for M22. Here's a new example. We've had a look at this set of 4 elements from the set of quartic polynomials, right? So this is a subspace, and we've shown that this set is a spanning set for W. Okay, since the span of S is equal to W, and since S can be written as sort of these 4 factored polynomials, it's quick to see that S is linearly independent. Okay, so we see therefore that S is a basis for this set of polynomials such that polynomial evaluation at x equals 2 gives you back 0. Okay, so this is sort of a pretty cool relationship and sort of a pretty quick and easy way to cook up a basis if you want to ensure that one value in particular is equal to 0. Okay, here's another example. We've previously seen that this set Q of 2 matrices is a spanning set for this subspace of matrices such that there's two relationships between the values in the matrix that are equal to 0. Okay, so we now show it's a basis, right? So we've shown that it spans the subspace. Now we just have to show that it's linearly independent. So like usual, we'll consider a relation of linear dependence on Q. So here's that relation of linear dependence on Q. Alpha 1 times the first vector plus alpha 2 times the second vector is equal to 0. And we see that's true if this 2 by 2 matrix is equal to the 0 matrix. Well, certainly the only way that this is true is if alpha 1 is 0. And certainly the only way this is true is if alpha 2 is 0. So it must be, therefore, that alpha 1 and alpha 2 is 0. And we see the only relation of linear dependence is trivial. Okay, so Q is therefore linearly independent, and hence Q is a basis for this subspace Z. We previously saw that this set R, 1, 0, 6, 3, is a linearly independent spanning set for the crazy vector space. It's therefore a basis. Okay, and again, we looked at this set previously when we were looking at the crazy vector space in section LISS. Okay, let's talk a little bit about bases for spans of column vectors. We know, for instance, that theorem BS tells us how to write a new set T that's linearly independent such that the span of T is equal to the span of some set S. Okay, we now know that this new set T that's linearly independent and spans is a basis. Okay, and this is also true for theorem BCS, which is just an application of theorem BS to the columns of a matrix. We know that the basis of a row space and the basis of a null space also give us a linearly independent spanning set. So those theorems are actually giving us a basis for those subspaces. Okay, so here's an example. These 4 vectors in C3 are definitely linearly independent. We'll go ahead and identify a smaller set T for which the span of W, oh no, this is W, not the span of W, for which W is equal to the span of T. Okay, so the way we'll do that is just by applying theorem BRS, basis of row space, to a matrix. So here I have created a matrix that has those vectors as the rows. We know that doing row operations doesn't change the span of the rows, so that here I'm not changing the span of the row space. These 2 vectors are linearly independent, and they have the same span as W. Okay, so this set 1, 0, 7/11 and 0, 1, 1/11 is a basis for W. Now, it's sort of customary to remove fractions, so you can always multiply through by a scalar, of course, and not change the span at all. Okay, so multiplying through the first vector by 11 and the second vector by 11 to remove fractions gives us another basis for W. I'll call it T prime. Okay, let's talk about bases in non-singular matrices. So here is the theorem. Suppose that A is square in size M. Then the columns of A are a basis of Cm if and only if A is non-singular. So the proof is pretty straightforward. We'll set the set B to be the columns of A. We see that B is a basis for Cm if and only if, by definition, right? If and only if B is linearly independent and spans Cm, which is true if and only if A is non-singular. Okay. So here is an example. The matrix associated with archetype K we know is row equivalent to the identity. Therefore, the columns of K are a basis for C5. Okay, it's not totally clear why you would want to use this basis, but this is a basis for C5. Okay, so here is an addition to our non-singular matrix equivalency theorems. We've added this one statement that columns of a non-singular matrix are a basis for Cn. Okay, and again, that's sort of exactly a result of being linearly independent and spanning Cn. Okay, so let's talk a moment about orthonormal bases and coordinates. So it turns out that when B is an orthonormal basis, any element of W can be written as a really quick linear combination of B. So this is a super useful theorem. Remember that orthonormal means two things, right? Orthonormal means an orthogonal basis, which is also full of unit vectors, right? So each of those vectors has norm 1. Okay, so let's start off by thinking about a theorem we had last time. So here's the theorem about coordinate representations. When B is a basis of W, any vector W in the subspace W has a unique coordinate representation relative to B. Okay, so that coordinate representation can be represented as alpha 1 V1 plus alpha 2 V2 all the way out to alpha P VP. Now, in order to get the representation that you want, we're going to go ahead and have a look at the inner product of the ith orthogonal basis vector with W. Okay, so here I'm thinking about the inner product of the ith vector in our basis with W, and all I've done is substitute this expression for W in our inner product. Okay, now it turns out that there are distributive properties of the inner product, so I can write the inner product of a sum as the sum of the inner products, and I can pull scalars out of the inner product. Okay, so here are those properties, right? The inner product of a sum is the sum of the inner products, and then scalars can be factored out of inner products. And remember, the fact that the basis is orthonormal means that first, it's orthogonal, so that the inner product of any two different basis vectors is equal to 0. And moreover, orthonormal means that when you take the inner product of the same basis vector, you get back 1. So this whole linear combination here, or this whole sum, I guess, of alphas reduces to 1, and the ith alpha is just equal to the inner product of V sub I with W. Okay, so we see therefore that that alpha 1 is V1W, alpha 2 is V2 with W, all the way out to alpha P, which is VP with W, and that's the end of the proof. Okay, as it turns out, it's sometimes annoying to deal with an orthonormal set, but this game also works if the set is merely orthogonal. And in the case where the set is merely orthogonal, it turns out that the inner product of V sub I with itself is not 1, and there's a norm squared down there that you're dealing with in the denominator. But a very similar argument works out. Okay, so I'll have you illustrate that in this example. We previously found that this set is orthogonal, and we'll want to represent V as a linear combination of vectors in T. Okay, so again, the way that we'll do this is by first writing V as an inner product, or writing V as a linear combination of the U's, and then recognizing that the U's are orthogonal. Okay, so here are those coefficients. Again, since T is an orthogonal set, we know that alpha 1 is the inner product of V with U1 divided by the inner product of U1 with itself. Alpha 2 is the inner product of V with U2 divided by the inner product of U2 with itself. And alpha 3 is the inner product of V with U3 divided by the inner product of U3 with itself. And I can't sort of describe how valuable this is for the first time ever when we're going to express a vector as a linear combination of other vectors. We don't have to solve a linear system. Okay, so this is super powerful, a really important leverage of orthogonality. Okay, the last thing I want to mention is just the theorem that that when B is an orthonormal basis and C is a new basis, a new set that you get from multiplying the matrix A by all the vectors in the basis B, it turns out A is unitary if and only if C is orthonormal. So this isn't something I'm going to go into, but you can cook up a new orthonormal basis multiplying an old orthonormal basis by a unitary matrix. Okay, that ends up being an important result. Okay, folks, that's it for this section on bases. I hope you have learned something interesting, especially about the importance of orthogonal vectors. Have a great day, and we'll see you next time. So long for now.